Did the universe have a beginning? Today, I have two of the world's leading cosmologists to debate this fascinating question. Firstly, leaning towards the affirmative that the universe did have a beginning, we have Thomas Herzog, professor of theoretical physics at Leuven University. He was one of Stephen Hawking's closest collaborators. He's also author of the recent book on the origins of time. So, welcome, Thomas.
Hi, Phil. Well, pleasure to be here.
And in the opposite camp, we have Robert Brandenberger, who is the Canada Research Chair Professor of Physics at McGill University. He's perhaps best known for developing string gas cosmology alongside one of the world's leading string theorists, Cumrun Vafa. So welcome, Robert.
Thanks for having me.
Okay, so now before we kick off, both Thomas and Robert have starred in some of my cosmology documentaries. So if you want to see more of those, do click on the channel's cosmology playlist. And they both appear in my upcoming book, Battle of the Big Bang, which is about competing models of the very early universe. It's co-authored with Nihaya Shafshordi, and you can just start pre-ordering it now. There'll be a link in the description below. But enough shameless plugs. Why don't we get to know our guests a little bit before we launch into the debate proper? So Thomas, why don't we start with you? Tell us, how did you get involved in early universe cosmology? And what was it like being Stephen Hawking's PhD student?
I got involved in cosmology because of Stephen. I guess in the 90s, I was advised to come to Cambridge, which was a mecca for theoretical cosmology at the time. And I got to know Hawking and Turok and fellow eminent cosmologists. And I was just very much interested in this field from the start. I guess as a young boy, I was interested in maths, but also philosophy. And these two fields seem to come together when you talk about the Big Bang. And I just thought it was very fascinating. And Stephen was one of these rare cosmologists, I think, who was very much driven by the idea of tackling age-old philosophical questions using modern scientific methods. And I was hooked from day one.
What about you, Robert? How did you get involved in this area of physics?
Right, so I got involved in a very different way. It's by accident. So I started out in graduate school in mathematical physics. So constructive quantum field theory, a very mathematical sub-branch of physics. And but then one spring, a friend of mine, Jenny Trashern, who was a fellow student, she suggested that some of us ought to do something over the summer which no one with a PhD knew about. And she had come across an article by an unknown physicist by the name of Alan Guth. This is actually the original article on inflation. And so over the summer, we taught ourselves the material to be able to understand this article. And this was rather fascinating. So instead of just listening to lectures and thinking about things which other people had done decades ago, it was thinking about things which were new. So at the end of the summer, I went to my advisor, Arthur Jaffe, mathematical physicist, and I asked him, is it possible for me to do my PhD in cosmology? And then he said, fine, as long as I don't have to read it. And so this is the way that I got into cosmology. I was actually at the right time, at the right place. I was very lucky. I don't regret going into this direction at all. It's fascinating. It was fascinating when I started, and it's still fascinating today.
So in the 1960s, we got a lot of evidence that the eternal steady-state theory of Hoyle, Bondi, and Gould is wrong, and the Big Bang theory of Friedman, Lemaitre, and Gamow is right. But did that prove that the universe had a beginning? Robert, why don't you sort of give us your thoughts on this?
Right, so my short answer is no. But let me elaborate on that. So the standard Big Bang theory or model was initially a bad word. So it was a pejorative term. In fact, I was told by Slava Mukhanov the story of Zeldovich, that when he heard about this idea of the expanding universe, the standard Big Bang, he said that this cannot possibly be right, because if it were right, there would be a microwave background. So now, afterwards, the microwave background was actually discovered. So we know that the standard Big Bang theory explains the evolution of the universe 13 billion years into the past. It might not explain the evolution beyond that. So if you take the standard Big Bang model and you go forwards in time, then you find that the microwave background was produced 300,000 years after this hypothetical Big Bang. And so we know that standard Big Bang model has been extremely successful, but it doesn't explain everything. And in particular, it is based on general relativity, a classical theory, and it is based on describing matter in terms of classical stuff. And we know that at high densities, matter cannot be described using classical physics. And I think we also know that at high densities, the universe cannot be described by classical general relativity. So we know that there's a question mark that should replace the beginning of the universe in the context of the standard Big Bang.
Thomas, what are your thoughts on this? We'll come on to the Penrose Hawking theorems a little bit later, but just on this sort of observational evidence that we saw in the 1960s, with the CMB and the structure of galaxies, what does that tell us anything about whether the universe had a beginning or not?
My take on those discoveries is that they put the question of whether the universe had a beginning central in cosmology. I think it's important to realize that when Lemaitre and certainly Friedman, when they speculated on the idea that the universe might have had a beginning, this was extreme speculation, and it was also regarded as such. It was in a sense brilliant speculation, grounded in theory and clear intuitive thinking, but it was certainly an extremely wild extrapolation of what was known at the time. Simply the idea that the universe might once have been in a completely different state. That, I think, the discovery in the 1960s changed completely. The question became a scientific, presumably observationally interesting question, and so forth. So that's what it did to me. The meaning, I think, of those early of the discovery of the CMB.
Right. So then we get, the Penrose Hawking singularity theorems, also in the 1960s. And Thomas, in the film, we made a movie together. You can watch it on the channel on the Cosmology playlist. It's Thomas, it's Jim Hartle, it's Stephen Hawking. And in that movie, Stephen said, that these theorems proved that the universe had a beginning. Do you agree with that statement? And what is the case for that? What's your thoughts?
I think it's a typical Hawking sentence, right? So we have to be a little careful. Of course, within the realm of classical general relativity, these theorems prove that the universe had a beginning. But as Robert points out, we all know that classical general relativity probably won't apply in the earliest instances. So the real lesson of the theorems, of the singularity theorems, is that our classical notion of time probably ceases to be meaningful in these extreme conditions at the Big Bang or perhaps inside black holes. So to me, the theorem suggests really, okay, if you read that theorem strictly, you would be led to conclude that the actual beginning is a singularity and therefore not even part of science. Very few scientists have interpreted the theorem as such, right? We've pretty much all interpreted that as saying there's new physics, quantum gravitational physics entering in those early instances, out of which, presumably, one way or another, a fairly classical relativistic notion of time must emerge. So in that sense, the theorem is profound. It sort of says that even time is an emergent quality of the universe. Incidentally, baby versions of the Hawking-Penrose singularity theorems were already proven in the 1930s by the likes of Lemaitre upon the suggestion of Einstein, who of course understood immediately that the singularity would be a big game changer and potentially a big problem.
Robert, what's your take on these Hawking-Penrose, or is it Penrose-Hawking theorem?
I think I agree with what Thomas said. So I'm now teaching a class for non-science students called Space, Time and Matter. And when I introduce the Big Bang model and the singularity, I always look at the audience and ask, is there a mathematician in the audience? And then I'll say that for you, you can deal with singularities, you can prove statements about singularities, but no experimental physicist will ever measure anything which is infinite. So I think if the theory predicts an infinity, then it just means that the theories run up to its limit and it has to be replaced by something else.
But let me just push you on that, Robert, because isn't there an issue of, well, I don't like the infinite densities, infinite pressure, infinite curvature of a singularity, but suppose I removed it and the universe was eternal into the past. Isn't that another infinity? I mean, why do we prefer one over the other?
Yeah, this is a very good question. So maybe to go forwards to what you actually want to address towards the end of the discussion. So I actually think that there are limits of science. And I actually don't think that with pure science, with pure physics, we'll ever be able to definitively answer the question, was there a beginning of time or not? And as Thomas pointed out just before, it also, what is time? So the question of what is time, that's related to the question, was there a beginning or not? So, but back to what you said, if you have a model in which time runs from minus infinity to plus infinity, then you still have the question, what does the infinite time range mean? So you might have shifted the philosophical problem, but you've not eliminated a philosophical problem. But I think it's still interesting to explore whether models which are consistent with the data that we have and we will have in the future, whether they indicate a preference for one or the other scenarios.
Right. What's your take on that, Thomas? Is there how should we think about infinity? Like, should it be allowed in any sense, or is there a difference between the curvature singularity and saying the future could be infinite or the past could be infinite? Should they be treated differently or the same?
So in my younger days, when I was indeed, I grew up in the late, in scientifically in the late 90s, early 2000s, and people were talking a lot about eternal inflation, producing a multiverse, which is infinite in yet another sense, named spatially infinite. And at the time, it seems people were easygoing about all sorts of infinities. And as Robert indicates, I think we've come to realize that both curvature singularities, but also other kinds of infinities, infinite future, infinite past, infinite space, are really problematic. Certainly philosophically, but I would argue even scientifically, they're an indication in no matter which dimension you go into infinity, that something's wrong with either your assumptions or your theory or your viewpoint. And this is partly what I discuss in my book as well, right? So I do think that, and so I think first there's an alternative to which we can come later. But in the case of the infinite space, for instance, in the multiverse, and it became clear that this is a fundamental problem. It leads to the issue that such a theory is not even falsifiable. Not because, of course, we can't go from one bubble universe to another, but because you don't even make unambiguous predictions for where we should be and therefore what we should be observing in such a universe. So in that case, I think it's clear that the problem is both philosophical and scientific. It's philosophical because you've disconnected your theoretical framework from the simple fact that we have an observer's viewpoint from within the universe. It's scientific because science should be able to make unambiguous predictions, let alone whether you can verify this. That's a different matter. And so somehow I think infinities, as Robert says, are always indicative of you having pushed your theoretical framework, whatever it is, beyond the limits of its reach, of its domain of applicability. So in a sense, for us theorists, they're an important guideline.
But let me just push one last on this. I mean, so you mentioned eternal inflation, and clearly in that framework, lots of bubble universes, there's an issue of, how do you make predictions? What should our universe look like? And that's covered in your book. But even if we don't go to inflationary cosmology, which we're going to come on to in a second, presumably the universe could be spatially infinite. I mean, we can't just rule that out a priori, or can we? Robert, what do you think?
I would say we cannot. Now, when we think about these questions, I think every one of us physicists, we come with some preconceptions which come from our education and from our everyday experience. And I think from our everyday experience, I think it is easy to conceptualize infinite space. For me, it is also easy to conceptualize infinite time. But that's a statement of the background I come from.
Right. Well, let's move on to inflationary cosmology. So, in the late 70s, early 80s, Alan Guth proposed inflationary cosmology, which is this exponentially fast expansion of the universe. There's also a theorem called the Bordet-Guth-Vilenkin theorem, which says inflation, can't have been going on forever into the past. Some people have argued that this proves the universe had a beginning. So does it? Robert, what's your take on this and on inflation in general?
Okay, so first of all, what about inflation in general? So I think we do not need inflation in order to explain the data that we have now. There are good alternatives in the market. And I would actually claim that at least the inflationary models, the way that we treat them in terms of physics, they are sick. They are non-unitary and violate the second law of thermodynamics. So, but let's leave that aside and come back. Let's assume that there was inflation. Then what's the status of this Bordet-Guth-Vilenkin theorem? So I view that as a small extension of the Penrose-Hakwing theorems. It extends the applicability of the theorems to matter of the type which is used to drive inflation. So I think I accept what the theorems tell us, that the inflationary phase had a beginning. And before that, there was something else which obeys the usual Penrose-Hakwing theorems. But again, in the past of that, there are infinities, and those infinities tell us that we need a better theory.
Right. But the claim that this theorem, the Bordet-Guth-Vilenkin theorem, proves an absolute beginning of time, what would you say to that?
So it's not true in the same way that the singularity theorems of Penrose and Hakwing address this issue.
Thomas, what's your thoughts? Do you think we need inflation? And if so, does it tell us anything about the beginning of the universe? Whether it had one or not?
I guess I'm more sympathetic to inflation as a paradigm or as a as a phase in the early universe. I guess the match between the observed CMB fluctuations, the temperature anisotropies, and the general predictions of inflation, I guess that has left just a big impression on me. I find it, perhaps this is a bit biased, but I find it a plausible, elegant mechanism to generate those fluctuations. But then on the Borde-Vilenkin theorem, I completely agree with Robert. It's an extension of Hawking-Penrose, and it should be interpreted in the same way as Hawking-Penrose, as we already discussed. It's indicative of something deeper, a deeper layer being there. That said, the simple fact that our classical notion of time can't go back all the way, must have ceased to be meaningful, is a very strong. It's not just like a small thing, right? It's a serious thing. It means that essentially the classical notion of space-time is too limited to describe the earliest phases. So this is a big thing. It means like genuinely quantum gravitational physics of one sort or another must play out there, must be relevant there, and ultimately either predict the origin of inflation or predict the expansion in some other way.
We're going to come on. I want to, Robert, go ahead.
Yeah, so I completely agree with what Thomas said regarding the theorem, but I'd like to say something about inflation.
Yep.
So the conditions that will give the microwave background fluctuations, these beautiful curves, they were well understood 10 years before inflation. There are important papers by Zeldovich and Zunyaev and by Peebles and Yu who point out that if the early universe satisfied three conditions, that then you get all the beautiful data. And so what inflation is, it's the first causal way to get a model which gives us the three conditions. But now there are other models that have been proposed which yield the same three conditions. So after I've seen these beautiful papers of 1970 by Zeldovich, Zunyaev, and Peebles and Yu, I basically don't accept when people say that acoustic oscillations in the microwave background prove inflation.
All right, Thomas, what are your thoughts on, some people have said, what Robert just said, that these features of the microwave background, yes, they may be predicted by inflation, but they were predicted before inflation. So it's not really convincing evidence of inflation. What are your thoughts on that?
I agree that so far, inflation probably is not a unique way of generating these patterns. As Robert says, the patterns observed come down to 2 or 3 clear conditions, which for which inflation is an appealing mechanism, I guess, but probably not the only one. I guess there are two things to say following up on this. Observers are not done yet. There might be a pattern of gravitational waves showing up one day, and then their consistency relations or not, and then indeed alternatives to inflation may become more prominent and more important. The other thing is more personal. All these theories, alternatives to inflation and inflation, struggle, as we have been discussing, with the actual beginning, the actual origin. How do you get a universe in the first place? How do you think about something which replaces the singularity of Hawking, Penrose, and so forth? And of course, there I'm again somewhat biased. I do regard the model that I developed with Hawking. At least it's one model that.
Well, Thomas, that's our next topic actually. So why don't we get you to unpack? So you've developed with Hawking and Hartle their famous no boundary proposal. They proposed it in the early 80s, and you've worked on it and published many papers on it. Can you and if people want to learn more about it, they should watch the film that I made with Thomas and Stephen and Jim. But could you give us like the short Cliff Notes 2-minute summary? What does the no boundary proposal actually say happens before inflation, if inflation did happen?
Well, no, what I was about to say is that the no boundary proposal for the which is a quantum model for the Big Bang, which replaces the classical singularity, it predicts inflation, and it doesn't predict anything else as these early stages. So it goes very well together with this. In fact, it's I would say it's sort of the quantum counterpart or the Euclidean counterpart to what we call inflation or accelerated expansion. So, of course, that's theoretical bias, but I guess my main problem with alternatives to inflation is not so much at the level of the predictions so far. I do agree there are various alternatives, but to do with the more fundamental aspects. How do you actually complete those models into a theory that does genuinely resolve the singularity problem?
Right, Robert, before we come back to you, Thomas, though, could you just outline, like for the layperson, what does the no boundary proposal say happened if we go back 13.8 billion years? You mentioned this phrase Euclidean, but I don't know that people will be familiar with that. Can you unpack what Euclidean means and what does the no boundary proposal really say happened 14 billion years ago?
Well, I guess one way of describing the no boundary idea is that in the earliest stages of the universe, time and space themselves became sort of fuzzy. So that the fuzziness of quantum theory, which we know from quantum theory and from particles, penetrated even into the realm of space and time. To the extent that both these dimensions, which are very different today, of course, began to mingle. And the proposal was by Hakwing and Hartle was that, hey, wait a minute, if time becomes fuzzy and maybe it starts to mingle with space in these earliest phases, that led to a new way of dealing with the singularity theorems, namely you turn time into a space dimension early on and model the Big Bang, the actual origin, as a purely spatial geometry. So time would, in a sense, have evaporated away early on. And the surprise has been that if you buy into that model, which is a very specific model, of course, but it's bad enough to try to come up with a model, then you find a strong link between this particular model and a phase of inflation. Only universes with a primeval phase of inflation can emerge from that no boundary idea at the bottom, so to speak.
Right.
Anyway, I mean, I don't want to take up too much time. But
Robert, what have you looked at the no boundary proposal? Do you have an opinion on it?
Well, let me start out by saying something very simple. So when we do theoretical physics, we have equations, and the equations tell us how to start with some conditions in the past and to produce conditions in the future. And so I view the no boundary proposal as a way to get the initial conditions at some finite time and then to evolve them into the future. So I think that probably it's obviously the no boundary proposal is something much more fancy, but it's something that gives these initial conditions at a fixed time.
So
yeah, it also shows that it's a strange thing, right? As Robert says, it's a theory of initial conditions, whereas normal theories in physics are theories of evolution. So it is.
But one thing is that if you want to get inflation out of it, you do need to introduce a scalar field with the potential, which is quite fine-tuned. So you're not insensitive to, you are putting in extra stuff.
So does that make the theory less probable to be true? Is that what you're saying, Robert?
This is not a criticism of the no boundary proposal at all. It is just a criticism of the statement that inflation follows from it.
Right. So you could imagine the no. So are you saying you can imagine the no boundary proposal? Which, can we summarize it, Thomas, as this idea? If we want to summarize it in a sentence, that when we go back 14 billion years ago, instead of having three space dimensions and one time dimension, we have four space dimensions. I mean, that's sort of the big picture view of it. Is that a fair summary, Thomas?
Sure, but that sort of omits many things, right? Why four space dimensions? I mean, the idea of Hakwing and Hartle was four geometries with four space dimensions describe profoundly quantum properties of gravity. Whereas clearly we have three space dimensions and one time dimension. That's good for classical gravity. The singularity theorems, of course, insist on the time dimension being all the way there. So they insist on this very classical Lorentzian viewpoint. That's why they run into a singularity.
Right. But Robert is saying that you don't easily get inflation out of it. You've got to fine tune the scalar field, and so it's not so easy to get inflation out of the no boundary proposal.
That's right and wrong. If you don't have an appropriate potential, then you don't get anything out of the no boundary proposal. There will be no classical universe emerging whatsoever.
So, Thomas, sorry, let me interrupt. Can you describe what you mean by an appropriate potential? That may be a phrase.
The one that Robert was talking about. You need a scalar field with specific conditions in order to drive inflation in the first place. Yeah, you need only certain types of scalar fields will be able to drive inflation. If you don't have those fields, then sure, the no boundary proposal is not gonna magically produce inflation, but it's not gonna magically produce anything else either. It's just, it will be in that case, you have a wave function, which is a genuinely quantum thing, which has no cosmological relevance whatsoever.
So let me just.
It's a theory of the origin of inflation.
Right. But let me focus on this issue at the beginning of the universe, because one thing that came up in the film that we made, and I think it would be worth having you both comment on it, is that there's sort of two notions of time. There's real time, the sort of time that we're familiar with, real numbers that we're familiar with. And there are these things called imaginary numbers where, if you square them, they come to a negative number, which normally doesn't happen. And so the comment was made that the beginning of the universe in the no boundary proposal is in imaginary time, but in real time you have this eternal universe. So so there's a sort of a question as to how we should interpret. Let's presume no boundary proposal is the correct description of the universe. Is there a question of interpretation of whether it means there's a beginning to the universe or not? Thomas, can you just unpack that a little?
I don't understand the statement that in real time the universe would be eternal. That's clearly not true.
That's a comment. I should say that's a comment made from Aaron Wall. He said that the no boundary proposal only has a beginning in imaginary time.
Sure, but it's not eternal in real time. It would stop in real time, right?
Well, that's what he alleged, is that in real time it's actually eternal. I mean, Jim described a sort of bouncing universe that would appear in the no boundary proposal.
But also there, the arrow of time is finite in one direction.
Right. Okay. So you're saying that because there's a reversal of the arrow of time, that's still a beginning, right?
I think people have in the past read a little bit too much interpretation into this imaginary time business. Yeah. I don't find it particularly helpful.
Okay.
The originality of this particular approach to quantum gravity is that geometries with four space dimensions can capture certain coarse-grained properties of a true quantum realm. Their interpretation is very, very difficult. You want to go there in this four space-like geometry, you would be profoundly quantum and confused, and it would not make sense. So I view it more as the statement that if we go back in time, our usual notion of time becomes more and more fuzzy. So the notion of evolution, the notion of causality becomes more and more fuzzy. And a way to model this, that's the genius of Hawking, which he first tried out on black holes, right? The way to model this is to use these purely spatial geometries.
Right.
But you
Robert,
end up with something bizarre. You end up with a theory of initial conditions, whereas all other initial conditions in life and in physics are boundary conditions which we impose.
Robert, do you have any thoughts on this issue of imaginary time? But also, I want to talk about this notion of a reversal of the arrow of time, because Thomas is saying, well, there's still a beginning. But I know, like other people, Don Page, Alan Guth, Sean Carroll, they've said this is not a beginning because the middle is just the middle. It's not a beginning. What are your thoughts on this?
So I completely agree with Thomas. For me, in this approach, there is a beginning of what we see as classical real time. And so there may be several branches, but in each branch there's a beginning of real time. And this is a bit different from maybe other approaches to the initial conditions for classical evolution, which we might talk about later.
Right. Well, why don't we come on to that? Because you've proposed this model, String Gas Cosmology, and also you have a sort of a newer version, the matrix model. Can you explain what are these models, and brief description of what they are, and what do they mean for whether the universe has a beginning or not?
Right. So I actually believe that in order to really make progress at understanding the universe at highest densities, we do need to work from top down, not from bottom up. So we need to ask, what is the theory or the best candidate for theory which can describe all forces of nature quantum mechanically? So the universe has lots of matter in it, and as we approach the classical Big Bang singularity, not just the curvature blows up, but also the density blows up. So I believe that the starting point ought to be a theory which unifies all forces of nature at a quantum level. And so the only candidate that we have that does that is superstring theory. So that's indeed our starting point. And good. Now, having said that, the problem is that superstring theory is in development. It is not a well-established theory. And let me make an analogy with the theory of particles. So everyone knows how particles move classically. They are described by Newton's laws. We also know how particles scatter quantum mechanically. But if we want the real theory of particles, then we need notions which are different from particles. They are fields, quantum fields. And particles are localized excitations of these quantum fields. So now, the idea of superstring theory is that the building blocks, the classical building blocks of nature, are fundamental strings and not point particles. And over the last 3 decades, we've learned how strings scatter quantum mechanically. But we don't have the analog of field theory. And so basically we can proceed in 2 ways. We can either try to develop a toy model of the early universe, which is based on taking some fundamental principles that differentiate between point particles and strings. And it's these ideas which gave rise to Sting Gas Cosmology. So if you take a classical space and you replace point particles by strings, then strings have oscillatory excitation modes, which point particles do not have, and strings also can wind space. And this then gives rise to what Vafa and I did. But let's go the other direction, the more ambitious direction. So in the late 1990s, there was a proposal for what this unknown theory is that gives the non-perturbative definition of superstring theory. And this is a matrix model. No space. There is time. And you see, now comes my philosophical bias. And it's a philosopher would, I'm sure, vehemently object to my bias. Basically, the philosopher would say that my bias comes from not having studied philosophy and having studied too much classical physics. So this new model is a matrix model. The fundamental ingredients are matrices, n by n matrices, where this n goes to infinity. There's a time, there's a Lagrangian. So it's something that we naive physicists can deal with. But you see, I've stuck in the philosophical bias of having a quantum mechanical model. So there's a time. Okay, now what we've done is we've taken this quantum mechanical matrix model and we've stuck it in a finite temperature state. Now we've lost the time evolution. And our approach is to get everything out of this matrix model. So we have to get emergent time, we get emergent space, we get an emergent metric, and all of that. So this is a research program, and there are indications that what follows from this research program is a model in which when space emerges classically, it emerges with infinite size in 3 dimensions, precisely 3 dimensions. And there are fluctuations since we started in a thermal state, and these fluctuations, they give rise to the same predictions which Vafa and collaborators and I worked out in the 2006, 2007. So they are consistent with observations that we have now, and they give rise to a particular consistency relation for future observations with which it can be distinguished from the inflationary paradigm. So I think Thomas and I are in the same boat in the sense of replacing classical real time by something. We are just replacing it by something else. And again, we also agree on fuzziness of space-time, because this is also what happens in this emergent space-time. It is all fuzzy at the beginning, and then out of this fuzziness, it's exactly 3 dimensions of space that emerge.
And so basically, would I be correct to say the difference between inflation generates fluctuations from quantum fluctuations in a cold vacuum, and you're generating them from thermal fluctuations in a hot state? Is that right?
Right. In terms of fluctuations, that's the key difference.
Right. But then let's just go back to this issue of beginnings. What is it, if I were to ask you, does this model have a beginning of time, or does it not have a beginning of time?
Okay, so in this model, the time that emerges runs from minus infinity to plus infinity.
Right. Okay. Thomas, have you had a chance to look at this model? Have you looked at Sting Gas Cosmology, its predecessor, or just alternatives to inflation? What are your thoughts, Thomas?
Well, I looked at Sting Gas Cosmology, the predecessor of the models that Robert described, yes. But listening to Robert now, I was just wondering whether you are at risk of running into a measure problem when space is infinite.
So hang on, we should just explain for the viewer, the measure problem is this issue of how do we make predictions if you have infinities? So if I have a finite deck of cards, I can predict, what the probability of getting an ace is. But if the deck is infinite, what's the probability of getting an ace? Well, it depends on how you order the deck. Is that a fair description, Thomas, of this measure problem?
Yeah, well, in the case of cosmology, ordering the deck means you and me and Robert agreeing on who we are or where we are. So it's a profound issue. I guess, Robert, you're thinking of a fairly homogeneous universe, or statistically homogeneous universe, or...
Well, you see, what we can, given our starting point, we can actually get an emergent metric, and we can compute its properties, and it turns out to be spatially flat. And modulo the fluctuations which are induced by the thermal fluctuations.
Yeah,
so the answer is I don't think there's a measure problem at all in this.
Yeah, I think the key point, it's not...
There are other philosophical problems, but I mean, there's the infinity of time, which you alluded to. But if time runs from minus infinity to plus infinity, there's still an infinity there. And this, so the way that this actually works in the matrix model is that we do calculations for finite size matrices, and then you get the continuum space-time in the limit where the dimension of the matrix goes to infinity. And it's only in that limit that time and space run to infinity.
So are there any other...
If you're happy with fundamental discreteness, then you would not take the n going to infinity limit, and then you would have a time with a finite duration in the past and in the future. But I don't know what happens at the beginning and at the end. So the philosophical problems remain even if I work with finite n. So I'm excited about this research program, not because it eliminates philosophical problems. I like it because it starts from a top-down theory. It starts from superstring theory.
Mm-hmm.
Thomas, what's your view on strings versus other competitors in quantum gravity, like loop quantum gravity or causal sets or Java lift shifts? Do you think strings is definitely the way to go, or what are your thoughts?
I think so, yes. And one truly remarkable prediction of string theory has been holography.
Right, that's what we want to come on to next. So great segue. Tell us about holography. Can you explain what is holography and what does it mean for these issues?
Well, I guess holography is one way to understand how quantum theory and gravity, quantum theory and relativity, which are seemingly at odds with one another, can in fact talk with one another and be consistent. I would say that holography is the discovery that quantum theory and gravity can be two very different descriptions in a different language with different quantities of the same reality. And one description is useful often when the other one is not, and vice versa. And I would say, yeah, and the surprise, of course, has been, and hence the name holography, that one of the two descriptions has seemingly one dimension less, the quantum description, right? Now you might say, well, how the hell is this possible? Intuitively, the reason that quantum description gets away with one dimension less is because quantum theory can store information in a different way, in a more intricate way. It can store information using entanglement, so in a non-local manner. So the extra dimension that gravity needs is sort of stored in non-local information in the quantum description. Now, the key point to me is that when you start thinking about how these ideas of holography, which came out of string theory originally, came out of a top-down construction in string theory, how do they apply to cosmology, to an expanding universe? And the very first question is, which one of the dimensions is gone? Is the holographic one, is the one that holographically pops out of a quantum description? You find out that it's the time dimension. And of course, the time dimension is the one you're obsessed with, certainly the beginning, and the one which has been indeed the problematic dimension since 90 years, right? Since the discovery of the expansion of the universe, since the singularity theorems. If you're going to truly understand, and we've mentioned this, if you're going to truly understand the origin of time, the beginning of time, you're going to have to invent some sort of physics which doesn't rely on time being an a priori entity, right? The thermal state of Robert or the no boundary proposal. There are not many proposals out there, but I do think this is the way to go. If time is an emergent quality, it should emerge from something more fundamental. So this is another angle which made me more convinced of the no boundary construction, which is that Stephen and I at some point discovered a close connection between the no boundary wave function on the one hand and these ideas of holography on the other hand. From a holographic viewpoint, you go, what is that business with the imaginary time that you mentioned before? Because which I didn't want to answer because it's so vague. From a holographic viewpoint, the holographic screen would be much like the universe today. And you would go back in time, reconstructing the past history. You would do so by taking a fuzzier and fuzzier view on the hologram. So going further back into the past, you would erase more and more information from the hologram. You would just retain the few large-scale features. From this perspective, you come to the beginning, you come to the Big Bang, because you, at some point, you take such a fuzzy view on the hologram that there's no information left. That's the end point of your past reconstruction. And so the Big Bang, the beginning, the origin of time, becomes almost like an epistemic horizon. The holographic laws of physics simply don't take you further back into the past. It's sort of, they run out. In a sense, it would also be the origin of the laws of physics themselves. So I claim, this is just a hypothesis, of course, but I claim this is not just a scientific theory, but that it also is one that resolves some of the deep philosophical issues we've been mentioning, associated with infinities or with the origin of time.
Can you just unpack that a little before I put it back to Robert? Which philosophical issues are you talking about? The issue of the infinity of time and space, or are you talking about other? Because I know in the book you talk about this claimed anthropic coincidences, that constants of nature are fine-tuned.
Oh no, I was not really thinking about
going there.
Philosophical issues like, the infinities are gone, right? Because it's all very much finite. But I guess also the simple idea of where do these laws of nature come from? No one ever gave a clear answer to this, right? Are they mathematical truths that transcend the universe or not? And indeed, where's the observer in those? But that was predominantly a problem for multiverse theories, of course. So, and in fact, our model, our thinking, our hypothesis emerged from taking these philosophical problems with our cosmological theories, I guess, a little more serious than most people.
Right. And how exactly? No, let me put it back to Robert. What are your thoughts on holography? And this seems to be contrary to what in your model you're saying. Time goes from minus infinity to plus infinity. What Thomas is saying is no, time disappears when we go back 14 billion years into the past. So we're in a sort of timeless state. How do you sort of square this?
Okay, so the model of holography from string theory, which has really been worked out in detail, verified by many calculations, this is the correspondence between a space with negative cosmological constant and a boundary theory which has time running from minus infinity to plus infinity. So in this approach to holography, the famous Maldacena construction, there is a time which does run from minus infinity to plus infinity. Now, I may be wrong, but so what Thomas says is very exciting, but is the level at which these correspondences have been worked out, is this as rigorous as for anti-de Sitter space? So I don't know the answer to that. I thought the answer was no, but I may be wrong.
Right. Thomas, do you want to comment on that? That in the boundary, is it in the boundary theory, the other side of the holographic equation, time runs from plus infinity to minus infinity? So that would imply that.
Oh, no, that's not what Robert says, right? Robert says that in the top-down setting where holography has been discovered by Maldacena and Susskind and so forth, indeed, this is a universe which is very different from our expanding universe. It's more like a gravity box, and it has negative dark energy and so forth. In that context, holography works very differently, and it does different things. In the context in which I was talking, it's a generalization, if you wish, of the old Malacena correspondency, which indeed is less developed. It's more, the tools, the dictionary, the detailed construction is still under development. But the broad conceptual scheme, I believe, is clear. And in particular, the fact that it's the time dimension that's the emergent one. Just like if you imagine a black hole, what would be a holographic description of a black hole? It would presumably be some theory living on the horizon surface. What's the radial dimension inside the black hole? It's not a radial dimension as usual, it's a time dimension. Time and space flip across the horizon. So even naively thinking about the holographic properties of a black hole, the surface entropy, which was discovered in the 70s, already suggests that there's something holographic about time. And that aspect is, and this is a little bit bizarre to my mind, that aspect is absent in the old Malacena story. Now there's another version, again, a Euclidean version of the Malacena story, which is more closely connected to the holographic story of the boundary wave function. But so no, it's we're on the far fringes of physics, right? But yeah, you're asking these difficult questions about the origin of time. So what can we do?
Right. So just to clarify then, so the Maldacena conjecture was between an anti-de Sitter space. So that's the opposite of what we observe in our universe. We observe our universe has accelerated expansion. So this would be the opposite of that. We'd have a cosmological constant that would have the other sign. So that's where things are all worked out well, and we sort of understand it. But our universe has a different sign. So there things are a bit more uncertain. Is that
different sign and a completely different geometry? You see, anti-de Sitter space is like a fixed box, like a cylinder. Time runs and runs and runs, as Robert says. This is very different from our expanding universe.
Right, Robert. Let me take it back to you. So how do you make your model, the matrix model, with this infinite time back and forth, consistent with holography?
Okay, so there's a holographic ingredient, and this just comes from the fact that the basic objects in the theory are strings, and strings look like point particles in one dimension less. And this is actually a manifestation of holography. And you see that if you work out the density perturbations, then you can see that there's a holography that enters. So the thermal fluctuations of strings look holographic from the point of view of thermal fluctuations of point particles. So there is holography inbuilt via the strings, but it appears in a very different way.
Right. Well, let me go on to another topic, and that is this issue of entropy. So Roger Penrose, Sean Carroll, they've been raising this question of why was the entropy so low at the Big Bang, and how can we explain that? And also there's this question of, well, how could it be if you say, Robert, that time goes from minus infinity to plus infinity? How is it that we're not at like maximal entropy? What happened to the entropy if you go through the middle? Can you sort of unpack these issues for us? Robert, why don't you start us off?
Okay, I can try to unpack the first one. So if you have a prejudice that the universe starts out very small, let's say Planck size, and then you want to ask the question, how does our universe emerge? Then without inflation, you would never have as much entropy as we see today. So from this point of view of taking the equations and moving forwards in time, it looks like our universe contains an enormous amount of entropy. But now what Penrose and late Gibbons and Turok say is that if you work backwards from the present time, the present universe could contain much more entropy than it does. So now I have a philosophical bias of wanting to work forwards in time. And so from this point of view, I'm more sympathetic to the old view of the success of inflation, that inflation takes something with very little entropy and it produces something with a lot of entropy. Now, to get to the second part of what you're asking about, in our approach, we start with a thermal state. And so we start with a certain amount of entropy at a fundamental level, which is set by the temperature. And then we ask what happens in the future. And then we find that if the temperature has a particular value, which is not too, it's lower than the Planck temperature, then we get the right amplitude of density perturbations. So I haven't answered the question, where does that thermal state come from? And where does that amount of entropy come from?
But that's just an open. Hang on 1 second. So that's just an open question, then you're saying, Robert?
Well, we've stuck in the amount of entropy as an initial condition.
Right.
The amount of entropy in the present universe, or
in the present universe?
Yeah, because otherwise you probably face the problem that a smaller fluctuation or so would be more likely or probable. So a higher entropy, in other words.
Right. So we work in a fixed quantum state, and then we basically. So you're asking the question: how does a classical universe really emerge from a quantum state?
Yeah, and would it not be more likely or so to have a classical universe which thermalizes much sooner, or which has initially a higher entropy?
Okay, so if we just take averages, then that's not what happens. But I have to pass on this issue which you're raising. So that's a good question, and I have not thought about that.
Mm-hmm. Right. And other people have schemes where the entropy either like has some kind of reset that go from the pre-Big Bang universe to the post-Big Bang universe, like Penrose does. Others say there may be some observer-dependent effect. I think Carlo Rovelli advocates that point of view. Sean Carroll has a view that you could have low entropy baby universes popping out of a larger universe that's increasing entropy. How, in the no boundary proposal, do you sort of tackle this problem that Penrose raises?
Well, first of all, well, maybe this is my own line, but my interpretation of the issue that Penrose has repeated for decades is that inflation needs a theory of how it got started. Inflation itself does not solve the entropy problem or whatever. And it's probably, in fact, related to the origin of time problem, which it doesn't solve. So the no-boundary wave function is a theory of how inflation started. And it has the property that it, as a wave function, encompasses a whole bunch of possible universes. It does just not describe like a single universe. In any model of inflation, it will describe a universe with a lot of inflation and another one with no inflation and so forth. So it sort of doesn't, how should I say this? It has low entropy and high entropy universes in one wave function. So it's not that it sort of wipes out these high entropy universes entirely. And then the question is, well, wait a minute, in which one should we be, or how should we think about this wave function, or what should we be doing? And then you have to realize, and this was, I think, what much of our movie was about, right? What sort of question do we actually ask of a wave function of the universe? And you realize we are asking a question as observation, as entities within this wave function. We're part of this wave function, in contrast to all other wave functions being discussed in quantum mechanics. We are part of the wave function of the universe. And so Jim and Gell-Mann, they developed a whole sort of framework to ask, going back to Everett and John Wheeler, to deal with this thorny fact that we are within the wave function of the universe, and so to speak, we're carving out our reality within this. We're selecting a history, one of the many histories within this wave function. And that's a whole enterprise to sort of extract, learn how to ask the question we're actually asking from the wave function of the universe. And if you do so, you're finding that our past should have had a lot of inflation with a no boundary origin. But this is not to say that this is the most probable universe in the entire no boundary wave function. No, not at all. But we are not asking a global question, thinking about all possible universes.
Right. All right. Well, we're running out of time, so I just want to get to the very last topic, and that is a question of experiments. How can we experimentally probe further than where we are? Like, we know the universe in a very hot, dense state 13.8 billion years ago, but
Yeah, that's a very relevant question. Right?
Can we push beyond? That's question one. And then question two is, will we ever, and I think, Robert, you were saying no, but maybe we should just go back to that. Can we ever really answer this question from experimental point of view, which ultimately, I think physics is an experimental topic? Did the universe have a beginning or not? Because I think your matrix model is saying it's eternal into the past. I think no boundary proposal, Thomas is saying it doesn't. It has a beginning. So those two questions. Robert, let's go to you.
Okay, so the second question, I think that we will never really be able to answer the question, was there a beginning of time or not? However, we have models, so you've heard models which have a beginning of time and models which do not have a beginning of time. And each of these models can be worked out, and they can be worked out to the level that they make predictions for observables. And so we are making lots of progress in terms of observational cosmology. And hopefully we will soon measure the spectrum of gravitational waves. And these different models that we now have, some with, some without a beginning of time, they make slightly different predictions for the spectrum of gravitational waves. And for example, that there are consistency relations. So inflation makes a consistency relation. Our model makes a different consistency relation. So we will learn a lot. We'll be able to falsify lots of models that we have now. I think we will learn lots of new things. I think we now understand how space can emerge, at least. We will be able to answer the question, why do we live in a three-dimensional space? Data will provide new mysteries, and we will be able to make progress on these new mysteries. So we will learn a lot by studying models of the very old universe. And we will construct better models of the very old universe as well. The ones that we have now will probably fail. We will construct better ones. And we will probably learn a lot about the nature of particles and the nature of forces of nature by these cosmological experiments. So we will learn a lot. But I think the one question which we will not be able to definitively answer is, was there a beginning of time or not? So this is my view.
Right. Thomas, what's your view?
Yes, so I certainly agree that we have not reached the end of the observational program, right? I mean, the idea of mapping out the history of the universe with gravitational waves, which is going to play out in the 21st century, one way or another will surprise us and will probe these earliest stages as well, I believe. As to the question of the origin of time, I guess I'm a little less pessimistic than Robert, in the sense that even though we cannot probably access this directly, I agree with that, but our theories reshape the question. And it seems to me it is not impossible to hope that at some point we will land on what is such an elegant, consistent way of thinking about it. For instance, we've both made vague statements that somehow time, physical, classical time, should become fuzzy, should sort of evaporate, should sort of disappear in these earlier stages, or vice versa, should emerge. Well, it's not impossible to hope that that process of emergence, that we can grasp this and understand this, even though we won't be able to fully falsify it. And so I think when we understand this, the question itself, which is so puzzling now, and which has been swept under the carpet in many ways, the question itself might be reshaped. Because in the end, we're dealing with the question of what's the origin of time? We're dealing with the question of what's causality. Somehow we are saying that causality has limits. But surely, once we understand how to think correctly about it, we're going to learn something.
Well, thank you so much, both Robert and Thomas. You've been amazing. It's been so fascinating. And if you guys have any comments, please, we'd love to hear from you, and give us any suggestions for future discussions. And we'll see you next time. Thank you very much, guys.
Thank you for hosting us.
Okay.
Pleasure.